Precalculus, lesson 12.7. For me, this is technically lesson 12.7 again because I did two algebra lessons and a precalculus lesson back to back to back, and I think it's the one time that I didn't do as much checking of my settings, nor did I watch part of the first video before I went on to do the second. And yeah, my microphone was muted for all three videos. So, the good news is for you that I think I will be able to teach the lesson a little bit better, a little bit more efficiently, and yeah, so I can keep this lesson a little bit shorter for you. The homework is even much shorter. There's not very much that I need you to do from this lesson, so that's good. All right, so this is 12.7. And it's called Special Sequences and Series. Special sequences. Again, sequence being a list of things, and series. A series being the sum of the items in a sequence. And the first thing that comes up a little bit here, kind of first big topic, is Fibonacci numbers. Fibonacci numbers. Goes back to, I think, the 1200s, if I recall correctly. And it's this. By definition, it starts out with 1 and then 1. And after that, each number is the sum of the previous two. So if we add the 1 and the 1, we get 3. Now if we add 1 and 3, I'm sorry, 1 and 1, if we add 1 and 1, we get 2. We add 1 and 2, we get 3. We add 2 and 3, we get 5. 3 and 5, we get 8. 5 and 8, we get 13. 8 and 13, 21. 13 and 21, 34. 21 and 34, 55. 34 and 55, 89. And it goes on for there. But those are the Fibonacci numbers less than 100. And Fibonacci numbers show up in all sorts of interesting patterns, especially like in ways that you can combine things, a number of different ways that you can do things. It first showed up in identifying the number of different offspring of rabbits that you can get when you put certain constraints on the situation. But I think it even shows up with something like if you have a set number of stairs, and I forget the exact rules, but like you're allowed to take certain number of steps up at a time and a certain number of steps down at a time, and what are the number of different ways that you can take like steps up and down, up, down, up, down, 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 up, kind of a thing to eventually get to the top, and it always comes out to be Fibonacci numbers. When I took combinatorics, they showed up a lot as well, but what I think is even more interesting than the Fibonacci numbers themselves is something called phi. This is the Greek letter. This is a lowercase letter, phi or phi. You'll hear it said either way. And a couple ways of representing it. One way is if you were to solve the quadratic equation x squared minus x minus 1 equals 0, you would get 1 plus root 5 over 2, if I recall correctly. Do I have that? Nope. Yeah. Let me just do that on my calculator here and see. 1 plus root 5 over 2. Yeah. Or you can represent it as an infinite ongoing fraction, like 1 plus 1 over 1 plus, maybe I should put that 1 kind of more like here, just to kind of represent better, over 1 plus 1 over 1 plus 1 over 1 plus 1 over, and keep that going forever. And it's weird, but it's the exact same thing as this 1 plus root 5 over 2, which is approximately 1.618034. That's a rounding of it. It goes on forever, and it's actually the most irrational number out of all of the irrational numbers. This one is the most irrational. And what we mean by that is it is the hardest to approximate with a fraction. In other words, you need a bigger fraction to get a decent approximation, more so than even like pi. You know, you've probably heard like pi can be kind of approximated as 22 sevenths, which is okay, but not that great. Well, this one is even harder to approximate with a fraction than pi is. Um, and one of the ways that that shows up in nature is if you were to take something like a rose bush and the petals of a rose. And let's just say you were designing a rose and you were like, okay, well, how about let's just see. What if I tried putting a petal, rotating 90 degrees, put the next petal, rotate 90 degrees, put the next petal, rotate 90 degrees, put the next petal, rotate 90 degrees, and oh. Well, now my fifth petal is exactly overlapping my first petal. And so it's going to block all the sunlight, or is also just not going to be visible. So that doesn't seem to be a very good arrangement. What if we rotated 30 degrees and you did the same thing, but you would again be getting exact overlaps? What if you rotated like 22.1 degrees? Well, it's going to be better, but not quite ideal. And what it turns out is the mathematically best way that you could arrange things like the leaves on a stem or the petals in a flower is to rotate something like, what if we rotate something like pi over phi, or pi over 2 phi, or pi over 3 phi, and that's the amount that you rotate each time. And by dividing by some multiple of phi, you are dividing by the most irrational number that exists, and by doing so, you arrange the petals in such a way that you minimize the amount of overlapping that they do with each other, thus maximizing the amount of exposure that each individual petal gets. And it turns out that that is how it happens all over the place in nature. And yeah, but also shows up in things like the the logarithmic spiral of something like a chambered nautilus. Which how that works is if you start with a square that is 1 by 1, and then you add to it another square that is 1 by 1. Now, what's our width but 2? And so I'm going to add above that a square that is 2 by 2. Well, now what's our height but 3, because we have 2 plus 1. So now I'm going to add to that a square that has a width of, or the size of 3 by 3. But now what's my width? 3 plus 1, or the 3 plus 2, which is 5. And so I can add another square on there. And if we connect these with a spiral, I'm going to switch what I am recording here to this so that you can see that Fibonacci spiral going on. And so it starts there kind of toward the middle and then goes out from there. And you have the 5 by 5, the 8 by 8, 13 by 13, 21 by 21, and you'd keep going out like that in a logarithmic spiral that is based on the Fibonacci sequence. Okay, that's just kind of partially is kind of interesting stuff. It's just also something that you should know about and be aware of if you're going on to calculus, which the assumption in a pre-calculus course is that you're studying this because you'll probably go on to calculus. Then Fibonacci numbers are something that you should be aware of. I don't actually have any homework stuff that you're doing with it. Okay, next topic here. Next topic, I'm going to erase this and start it right about here. Next topic is Taylor series. And what these are is this mathematician is based on calculus. This is something that'll come up in probably Calc 1 if you take that. And what it turns out is that you can approximate any function with a polynomial. And in particular, a polynomial that is a series, an infinite series. And the farther you continue the series, the more, the greater amount of whatever function you're approximating, you will be approximating. And this is not the order that the textbook goes into, but I'm going to start with the cosine of x because I have something ready for a graph to kind of demonstrate what's going on with that. So, for example, we could approximate the cosine of x as this: the sum from n equals 0 to infinity of negative 1 to the nth. Now what that's going to do is going to flip the sign back and forth, times x to the 2nth. What the 2n is going to do is it's going to make the power of x go up in increments of 2 over 2n factorial. Now what that looks like is you expand it. When n is 0, you have negative 1 to the 0, that's 1. 2 to the 2 times 0, or 2 to the 0, or sorry, x to the 2 times 0, that's x to the 0, which is 1, over 2 times 0, or 0 factorial, which is also 1, and you're left with a 1 as your first term. But then when n is 1, you have negative 1 to the first. That gives us a minus. And then x to the 2 times 1, which is just x squared, over 2 times 1 factorial over 2 factorial. And your next term is when n is 2, negative 1 squared gives you the positive, or the plus there. And we're left with x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial minus dot dot dot, and that just keeps on going. So one application that this serves is if you wanted to approximate something like approximate cosine of. Now the assumption here is that we're dealing with radians. Approximate the cosine of 2. All right. Well, we can approximate that. Cosine of 2, that's going to be approximately 1 minus 2 squared over 2 factorial plus 2 to the 4th over 4 factorial minus 2 to the 6th over 6 factorial. 1, 2, 3, 4, let's go one more, plus 2 to the 8th over 8 factorial. And we can see what that is. So that's going to be 1 minus, well, 4 over 2 factorial is 2, so 4 over 2 is 2, plus 2 to the 4th is what, 16? And then 4 factorial, 4 times 3 times 2 is 24, so we have 2 to the 4th over 24, and that's 2/3, minus 2 to the 6th is 64 over 6 factorial, and that gives me a total for that chunk of minus 4/45. And we get plus, let's see, 2 to the 8th over 8 factorial. So that's plus 2 over 3/15. And what's happening here is when we have just the first term, we are too big. And then when we subtract, now we're too small. And when we add, we're too big. Subtract, we're too small. Add, we're too big. But we keep adding and subtracting smaller and smaller and smaller and smaller values, and we're getting closer and closer and closer and closer to the actual value. If we put all these together, 1 minus 2 plus 2/3 minus 4/45 plus 2 3/15, and we get negative 131 over 3/15, which is approximately negative 0.4 159. And if I take my calculator, and I'm in degrees right now, so I got to adjust my mode, set up to radians. And if we do the cosine of 2, I get negative 0.416. So the actual is negative 0.4161. So I'm pretty close. Yeah, tenths, hundredths, thousandths. I'm, yeah, very close. I'm what, 2/10,000ths off as far as how I have it rounded here. So it can be used for approximating exact values of things that otherwise could be tough to approximate. Graphically, what's going on is this. I'm going to go back to here, but then I'm going to go here. So what I have is this is just a graph of y equals the cosine of x. Okay. Now I'm going to overlay this with just the first two terms of the Taylor series. And what we have is this upside down parabola. Now you can see that close to the middle, it's a pretty decent approximation, but the approximation starts to break down a bit when you're around -1 and +1 for your x values. So if we add more terms, this is now the first three terms. Notice the approximation is pretty good, almost out to ±2 for your x values. Okay. Now I have out to the x to the 12th term, so the first, what, 6 terms? No, 7 terms. 2, 4, 6, 8, 12. No, the first 6 terms, yeah. Now it's this purple one, and notice it's really, really, really hugging the cosine graph, definitely up to ±4, and then pretty close, even out to plus or minus, what am I trying to say? Out to ±5, yeah. So these first three terms, it'll be a very, very good approximation out to, around, what do we say? Almost 2, but not quite. Definitely out to 1. And the farther out you go, the more that approximates. But it's also the Taylor series, the formulas differ depending on where you have it centered. And the formulas that we're dealing with here are centered at x equals 0. If you wanted to be able to get a better approximation with fewer terms, you could recreate the Taylor series, but centered closer to the value that you're wanting to approximate. So like if you wanted to approximate the cosine of 10.3, well, what you could do is you could recreate the Taylor series centered at 10, and then your approximation will need fewer terms to be a very good approximation than if you're dealing with the Taylor series centered at 0. You're going to have a bunch of the terms in order to get a decent approximation that is going out to an x value of 10. Anyway, so that's that. Back to that. And yeah, so that's our Taylor series for cosine. Then the textbook gives you two other Taylor series. I'm not going to bother putting them down here. There's one for e to the x, and then another one for the sine of x. And you'll have a few homework problems where it's like use the first 5 terms of the Taylor series to approximate like e to the 0.4, or use the first 5 terms of cosine's Taylor series to approximate, in this case, like we did this example, the cosine of 2. Okay? All right. That's the Taylor series topic. Next, we have Euler's formula. Euler's formula. And this kind of relates to the polar form of a complex number that we've seen. But here it is first, and we'll talk a little bit more about it. E to the I alpha, where alpha is some angle, equals the cosine of alpha plus I sine of alpha. So the assumption here is that we're dealing with a radius of 1, because that's our polar form of a complex number, that r cis theta, radius times the cosine of theta plus I times the sine of theta. So the context is we're dealing with what initially looks like the xy plane, but is actually the real axis and the imaginary axis. And it turns out that if we were to go with, I don't know, let's just say like 60 degrees here, with the radius of 1, okay, this is 60 degrees, that we could represent that, I should have done that a little bit bigger, but as a right triangle, where this side would be the cosine of 60 degrees, and this side would be the sine of 60 degrees, with an I tacked on because it's the imaginary axis. So this number here could be represented as 1 times the cosine of 60 degrees plus I times the sine of 60 degrees. Or if you did the math, cosine of 60 degrees is root 3 over 2. This would be root 3 over... No, cosine is 1/2 there. Cosine, this would be 1/2 plus root 3 over 2 I. Well, this formula says that that is the same thing as e to the I alpha, which alpha here. So usually, rather than degrees, you're going to see this in context of radians. So this would be pi over 3. E to the I pi over 3. In other words, this number, if we found the magnitude of this, the absolute value, you might recall we dealt with the absolute value of complex numbers. And I mean, it's kind of like this length, but it turns out that, yeah, that this is an alternate representation of this. Now, the main reason we bring that up in this context is because this. Let's say we dealt with, we plugged in pi. So we have e to the I pi. And let's look at what this expands to be. So the cosine of pi, well, pi is 180 degrees. Cosine of pi is -1. Sine of pi is 0. So we're left with e to the I pi equals -1. Or you can rewrite that as e to the I pi, if we added 1 to both sides, plus 1 equals 0. That formula right there is the one that a lot of mathematicians feel is the most beautiful formula of all formulas. The reason why, as far as elements of it, there's e, I, pi, 1, and 0. And then mathematical operations are going on. It has exponentiation because it's e to the. It has multiplication because it's I times pi. It has addition and it has equality. So it has ei pi 1, 0, exponentiation, multiplication, addition, and equality in one very compact little thing. But this left-hand side, we're going to do something with here by taking the natural log of both sides. We're going to take natural log of e to the I pi equals natural log of -1. Okay. Now we're going to use our power rule here to say I pi times the natural log of e equals the natural log of -1. Now, natural log of e, well, natural log is log base e. So we're saying e to what power equals e, and that's just 1. So we're left with is I pi equals the natural log of -1. Now, so far, we've said that you cannot take the log of a negative number. Because, like, if you're dealing with something like log base 10, right? Log base 10 of -12 equals what? Well, you're saying 10 to the power of what equals -12. And if you say 10 to some positive value, like 10 to the third, 10 to the fourth, 10 to the fifth, you're getting bigger and bigger and bigger positive numbers. If you plug negative numbers in here, and you said, well, 10 to the negative fifth, 10 to the negative sixth, 10 to the negative seventh. Well, that's just 1 over 10 to the fifth, 1 over 10 to the sixth. And you still are dealing with positive numbers. They're just getting closer and closer to zero. And so there's no real number that is an answer here, but there are complex numbers. And so what it looks like is this. If we did an example here, it might look like this. Find the natural log of, I'll just deal with this negative 12, sure. Natural log of negative 12. Well, do you agree that natural log of negative 12 is the same thing as natural log of 12 times negative 1? Now we can use our multiplication rule here and say that's the same thing as natural log of 12 plus the natural log of negative 1. Now the natural log of 12 you could do in your calculator. Natural log 12, and I get 2.48. 2.48 plus, well, what's the natural log of negative 1? But I know that over here, that is I pi. And that is my answer. So when you run into natural log of a negative number, it's just the natural log of the positive number plus I pi. And you'll have 2 or 3 homework problems like that that literally is just do the natural log of the positive number and add I pi. And that does it for this lesson. So again, I know there's a bit of explanation here, but yeah, it's just kind of stuff that should be on your radar, but that we're not doing much with directly at this point. And so that's why the homework should be pretty short. At least I hope that it is. Okay, hope it goes well. As always, let me know if you have questions. Bye.